Well, hello Internet, and welcome to my Haskell video tutorial. In this one tutorial, I'm going to cover a vast majority of what you would read in an average 300 to 400 page book on Haskell. And I'm going to have a special emphasis on lists and functions, and more importantly, those things that confuse people about Haskell. I've talked to a lot of students. I know what confuses them, and in this tutorial, I'm going to try to make everything very clear. Just so I can go over this quickly, Haskell is a functional programming language, and everything in it is immutable. So once a value is set, of course, it's going to be set forever. Functions can be passed as a parameter to other function. Recursion is used very often. Oddly, Haskell has no for, while, or technically variables, but it does have constants, and even though it doesn't have those things, it still is able to do quite amazing things. Haskell is also lazy in that it doesn't execute more than is needed, and instead just checks for errors whenever you compile, and the compiler is very, very strict and does its best to cut out any potential errors. Haskell, like Lisp, in my opinion, is a great language to learn if you want to get better at programming, just aside from the fact that it's a great language. So, enough talking, let's jump over and I'll show you how to get everything you need to install it. Okay, to install Haskell, or the compiler we're going to be using, we're just going to go to haskell.org/downloads, and then you're going to come over here and you're going to pick either Windows, OS X, or Linux, and everything is going to install for you. Just have to click on this, install it. And Windows users, you might need to put a path to the compiler in your path to get everything to work in your command line. And that is basically all you need. Just wanted to let everybody know there is a great book online, and it's free, and it is called Learn You a Haskell for Great Good. A lot of what I did here, I worked with some students that went through this book, and what I'm trying to do in this tutorial is both cover everything that's in this book. However, I didn't use it as a guide. I instead used the problems people had with this book to try to make Haskell more understandable. But once you watch this video, this is a great book and everything should be very clear and you can be able to go through it. And of course, this is not a sponsored link. So enough talking, let's write some code. Okay, on the left side of the screen I have a basic text editor. This is Text Wrangler. If you're on Windows, use Notepad++ or something like that. On the right side I have Terminal, or if you're on Windows, use Command Line. Everything, irregardless of what OS you are using, is going to work exactly the same. Now what you're going to want to do first in your text editor is create a file. You can name it whatever you want, but make sure it has the extension .hs at the end of it. And then we're going to come over to our terminal and we're going to load GHCI, which is going to allow us to compile everything. So I'm just going to type in GHCI, and there we go. Everything is loaded and ready to go on the right side of my screen. I'm also going to load this program over here, which doesn't have anything into it, and I'm just going to type in :L, and then I'm going to type in Haskell-tut, because that's the name of it. And now we'll be able to use everything inside of it. And we're going to be running everything just by going :R, and that's going to run everything on the screen. You're going to see that a lot. First thing I'm going to do inside here, well, if we want to have comments inside of our Haskell code, we just put a -- comments like that. And if we want to have multi-line comments, we put a curly brace and a dash, and then close that off with another dash and a curly brace. So there you go. Those are the two ways that you can comment in Haskell. We're going to import some modules, and modules are just a whole bunch of functions we're going to be able to use. So we're just going to go import data.list and import system.io. So those are the only two modules we're going to be importing. And now I'd like to talk about data types. Now Haskell uses type inference, which basically just means that it decides on the data type based off of the value that you store inside of it. However, you're also able to define what type of data, and you're going to see that here in a minute. Haskell is statically typed, which just means that once you define a type, you're not going to be able to switch it. And I'll just go through a couple of the different types we have here. First off, we have ints, which are whole numbers, of course, and your minimum number is going to be -2 to the power of 63, and your maximum number is going to be 2 to the power of 63. So there's an int, and you could actually check the maximum size. Let's go max int. There we defined our constant here, and let's say that I want to get the maximum size for it, and I'll be able to jump over here now and run this and then go max int, and you're going to see the maximum sized integer that we have here. And you could also do the same thing by coming in and doing min bound, and change this to min just so it's not confusing, r, and min int. and there is the smallest number you'll be able to use in an int like that. There's another type of integer as well, and it is just defined as integer. And this is what you're going to use most of the time, and this is actually an unbounded whole number, which means that it can be as big as your memory can hold. So huge. And you're going to see examples later on exactly how that's going to work. We also have floats, which are single precision floating point numbers, but for the most part you're going to use doubles for anything that's going to have decimals inside of it. And this is going to have precision up to 11 points, and I can demonstrate that. All programming languages come to a fault at some point in time whenever you're using floats, so this isn't anything specific to Haskell. So we could go, there's 11, and then always put a 0 in front of any of your floats that don't have any other whole numbers inside of them, and then we can go big float and see that everything adds up perfectly well. But if we put in another point of precision inside of this guy, and you're going to see things get a little bit wiry there. So just an example of how we're going to be able to use precision with our floating point values. Other data types include bool, which is either going to have a value of true or false. You're also going to have characters, which are going to be single Unicode characters, and they're going to be denoted with single quotes. Then you're also going to have tuples, which can store a list made up of many different data types. However, for the most part, when you're using tuples, they're only ever going to contain 2 values, and you're going to see more about why that works out that way later on. You can declare a permanent value of a variable, like let's say we want to go always 5, just by going like this and saying that it's going to be an int, and then we could of course go always 5 is equal to 5. And of course that's never going to change, and of course we can come over here and it's going to print out 5 if we ask it to print that. So that is the basics of data types, at least that we're going to cover here at this point with Haskell. Now let's take a look at some math functions. One thing that's really crazy, let's just go into a little example here. Sum of nums is equal to, we could come in here and sum a whole bunch of different values. So let's say we wanted to sum 1 through 1000. That is how easy it is to do. And you can see just that quickly, and with that one line of text we were able to do that. You're going to see a lot more in regards to, this is a list right here by the way, and it automatically generates values from 1 to 1000. We'll get more into the power of lists here as we continue. We're also going to be able to perform basic mathematical calculations here. So let's say we wanted to come in and do 5 plus 4. And of course there is a cheat sheet in the description as well as timestamps, so you'll be able to jump through this tutorial and pretty much learn whatever you want in the amount of time that you want to allot to this tutorial. So take a look at that as well. So we can come in here and run this, and of course we'll be able to go add EX, and it's going to pop that out there on our screen. Another thing that's important to know, however, is that there are prefix operators. So let's say we wanted to get the modulus of a division, which is just a remainder. Well, we would either go mod and then 5, 4 like that, and this is called a prefix operator because it comes pre to the actual numbers that we're going to be passing into it. This is just a function, that's all it is. You could, however, add backticks to this. So let's say we want to go mod ex2 and then go 5 and then backticks. This is up where the tilde symbol is, mod, and 4 to get exactly the same results. And you can see right there it returned 1 because that is the remainder of that division. And in this situation, this is called an infix operator because it's in between these two numbers. Pretty easy to remember. Another thing that's important to remember about Haskell, this is one of the weird things about Haskell, is if we wanted to do an addition with a negative number, we're actually going to have to come in here and put parentheses around it to figure that out because it would get confused if this is the subtraction operator or not. So just one of the couple different weird things about Haskell. Another thing that's interesting is, let's say we wanted to do a square root. Well, we could come over here and put colon and t and take a look at exactly what's going on with the square root function just that way. And this is very important to understand right here. Basically, what this is doing is it's planning on working with floating point numbers, very important. So that means if you want to use integers here, we're going to have to do something special, which I'll show you in a second. It's going to then receive a value and then pop out a value from that point on. And don't let that bother you if that sounds confusing. I'm going to give you examples, tons of examples that all of this is going to make a lot more sense. So what we're going to do here is let's define a number 9 and give it a value of 9. And we could say that this is an int just by putting in those colons like that, and then int, and then go square root of 9 is equal to, and then we could go square root, but because this is planning on working with floats, we are going to have to convert it to a float. Easy enough, just go from integral like that, and num 9. Now I'll be able to come over here and go square root of 9, and you can see that it gives us the square root of 9. Pretty simple. So if you want to ever need to convert from integer to a floating point integer, or a floating point data type, we're going to use from integral. Here are also a couple of other built-in math functions. There's a ton of them, but these are some of the ones that might be really important. So we can get pi just by calling for pi like this, or exponents or logs. We'll be able to do square or get the power of different values. We'll be able to truncate values, and we can just come in here and go like this. And you can see right there that it converted 9.99999 down to 9. You can also come in here and see how rounding works, which is going to be a rounding up of the value. And ceiling is also going to round up, as well as floor is going to round up. And here's a whole bunch of other different functions that are available inside of Haskell pre-built in. We're also going to have a whole bunch of logical operators. So we can go something like true and false equal to, and we're going to use uppercase T R U E, and then we can go and false to get those values, and we could also go true or false like this. And in that situation, this is going to be the OR symbol, very much like most other programming languages. And if you would want to get not equal to, you could just go not and true inside of it like that. And of course, we'll be able to come over here and say something like true or false and get the value of true. I'm sure you understand exactly how that works. I'm going to come back again. Let's take a closer look at how we're able to add addition with the addition function we have here. Again, we're just going to put :t, and again, you can see right here, the way this operator is going to work is it's going to receive 2 parameters, right like that, and it's going to return an outside value. So anytime you get confused about how a function works or the type of data types that we're going to be using, it also says that we expect nums, which are going to be either doubles, floats, ints, or integers. So that's all that's going to work with. You can see here a lot just on this one line just by putting in :t, and you'll be able to learn a lot about the different functions. So anytime you get confused, just check that out. You can also see, let's say we wanted to go truncate, just to see something a little bit different. You can see right here that it expects an a value, which is going to be a real fraction, which is going to be a decimal value, and it's going to return an integer. And you can see how the a's match up, right like that, and the b's match up with this guy right there. Now let's take a look at lists, which are very, very important inside of Haskell. Now lists in Haskell are singly linked, and you're only going to be able to add to the front of any other list. You're not going to be able to just jump around willy-nilly, but that's not really going to cause any problems. So let's say we just go and create a list. This is very easy to do. We'll just come in here and let's say prime numbers 5, 7, and 11. There you go. You just created a list. Now you're going to be able to concatenate these lists, and how we're going to be able to do that is go prime numbers and then concatenate with 2 pluses, and then you could just come in here and throw either a list name inside of here, or you're going to be able to type in a list itself, and there you can see the entire list printed out on the screen. You're also going to be able to come in here and use a cons operator to construct a list. This is very important to understand. It's very simple, but it's going to come up a lot later on. All we're going to do is put a colon between each of the list items that we want to combine, and then we're going to put an empty little guy there at the very end, which is going to show that that's the end of the list. And there you can see our list has been created. So remember this guy. This is a way to combine numbers into a list. This is one of the things that confuses people whenever they forget it. So just remember that guy. And if you printed out the cheat sheet, you might want to highlight it just so you can refer to it later. Of course, we're also going to be able to put lists inside of lists. 3, 5, 7. Put a comma between it, and there you go. And remember I said you can add values to the front of a list. So let's say more primes. 2 is equal to, and what are we going to use? The cons operator. We're going to put 2 in front of more primes, right like that. We can come in here and get the length of a list. Of course, put this on the next line just by going length, and then whatever list you want to work with. And you can see I got a little bit of an error. It's just saying not in scope. You're going to see not in scope a lot. That just means that it can't locate this name. And the reason why is I had it called more prime. Let's just call it more primes, and now it's going to work. And there you can see it compiled, and there you can see that we have 10 values inside of that list. Don't worry, when you're using Haskell, you're going to get a lot of errors because the compiler is very, very strict and safe. Haskell is considered to be an extremely safe language. We could also come in here and reverse our list. Very easy. Reverse prime is equal to, just by typing in reverse, more primes 2. We could also come in and check if our list is empty just by going null, more primes 2. Is list empty? Comes back as false, of course. We would be able to come in and get specific index values for it. So let's say we wanted to get the second prime inside of our list. We would just go more primes 2 like this. 2 exclamation marks like that, and then we'll put 1 because the first index, of course, is going to be 0, and then second prime, and you can see 3 comes back. We're also going to be able, and this might seem unimportant, but you're going to use these functions a lot. So you're going to be referring to this part of the cheat sheet a lot whenever you're writing programs. So let's say we wanted to get the first value, we would just go head, and if we wanted to get the last value, we could just go inside here and go last, and last prime. And you can see 29 comes back from there. We're also going to be able to come in here and get everything but the last value by going prime init like this. And you can see it popped out everything except for the very last value on our list. Remember our last, let's just do it. Last prime is 29. So there you go. We're also going to be able to come in here and get the first 3 values or whatever you want just by going take 3, first 3 primes, pop that back. We're also, of course, going to be able to return values left after removing specified number of values. So we can go removed primes is equal to and drop 3, remove primes. And you're going to see it's going to give us everything except for those first 3 values that we asked for. We're also very easily going to be able to come in and check if a value is in a list. So we'll say is 7 in list is equal to 7. And again, we want to put this in the middle. So we're going to make this infix. So we're going to put a backslash like that, or a back quote, and then we'll go more times 2 again, and then we'll be able to say is 7 in list. And you can see true comes back from that. There are tons of functions like this. We're also going to be able to come in and get the maximum value. So let's say we want the maximum prime. We'll just go maximum like that. And likewise, we're going to be able to do the same thing with the minimum prime for our list. Max prime's 29, min prime is going to be 2. I already showed you how to get the sum of all the values. You're just going to put sum before it and assign it to some variable or constant. We're also going to be able to get the product of values in a list, and the product, of course, if anybody doesn't know, is just the value all can evenly divide by. So let's go and create a new list here just to keep this simple, and we'll say 2, 3, and 5 is our list. And if we want to get the product, we can go product primes equal to, and then just go product new list, and there you can see it's 30. Just to reiterate here, we're going to be able to generate lists. So we'd say we want a list generated from 0 to 10. We just go 0 dot dot 10. And there you go, it's automatically going to calculate that for us. What's really cool is we could even come in here and let's say we wanted a list that's just made up of even numbers. We could come in here and define the step between all the different values by going 2 and then 4 and then dot dot 20. That's going to generate an even list. Let's come in here and show you exactly how that works. Even list. And there you can see, generated that for us automatically. We're going to be able to do all kinds of cool things with lists. We could even come in here and generate character lists. So let's say we wanted to come in and do A, and then we also, let's step through here. Let's say we wanted to have every other letter. We could do that. Dot dot Z. Very powerful list functions inside of Haskell. And there you can see, every other value popped out there for us. Another thing that's kind of cool is we're actually going to be able to generate an infinite list with Haskell. However, it's only going to ever calculate or create the list up to what you need whenever you need it. And that's what we talk about when we say Haskell is lazy. So it's basically going to just define that yes, indeed, this is going to be an infinite list. And there you go, just don't put an ending value. This indeed is a list that is going to go on forever. However, it doesn't have any need to create it until we need to, let's say we want the 50th item in this list. Then it'll generate the list up to that 50th item, but it will never go beyond that. Because of course it obviously can't create a true infinite list. But it does give you the power to work with numbers that are extremely large. We also would be able to come in here and repeat a value a defined number of times. So let's say we want to go many 2s, and let's just say we want the first 10 values. And this is just going to repeat 2 forever and ever until we tell it we don't want anymore. So many 2s, like that. Whoops, make sure you are that. Many 2s, and there you can see, generated 10 2s for us in that list. All this stuff doesn't seem important, but it will be important whenever we're trying to work with all kinds of ridiculously awesome functions like you're going to see later on. Replicate is also going to generate a value a specified number of times. So let's say we go many 3s. We could also go replicate and then 10 and 3 like that. Many 3s. And you can see it generated 10 3s for us. Also, cycle is going to replicate the value in a list indefinitely. So let's say we want to take the first 10 values, and then we'll call for cycle like this, and 1, 2, 3, 4, 5 like that. Cycle list. And you're going to say it repeated those items over and over and over again. And of course, we're going to be able to perform different operations on all values in a list. So let's say we want to multiply a whole bunch of different items in a list by 2. Well, we can just say list times 2, just to keep that simple. And what we're going to be able to do is define inside of here x times 2. This is the operation we want to be able to perform over and over and over again. Put the OR symbol inside of there. And then what we're going to say is we're going to pull a value out of our list. We're going to temporarily store it inside of the value of x. We're going to multiply it times 2, and then we're going to create a new list called list times 2 from that list. So let's say we want to multiply every value from 1 to 10 and then create a brand new list. We can do that. List times 2, and there you can see that was how easy that was to do. We could also come in and filter these results. So let's change this to 3, change this to 3. Now we're going to be multiplying everything in a list by 3, and then let's say that we only want multiplications times 3 that are going to be less than or equal to 50. We just put that little comma in there, and that's going to give us our results for that. So we'll say list times 3. And there you can see, gave us all the values, but those values less than 50, or less than or equal to 50 in this situation. And just to create something a little bit more convoluted, let's divide divisible by 9 and 13. That's a really crazy name. But we're going to come in here and we're going to say x, value of x that's going to go into the new generated list called this convoluted crazy name. And we're going to be pulling the x value out of our list. And our list is going to be made up of numbers between 1 and 500. And then let's say we want to filter these guys. So we only want values in which x modulus of 13 is equal to 0. So we only want values that are going to be divisible by 13 in this generated list 1 to 500 right there. And then if we want to put in another filter, we could just go x, and let's say that we only wanted modulus of 9, which is going to be equal to 0. So we want to go through a list from 1 to 500, and we only want values in which they are divisible by 13 or divisible by 9. And we wanted to come in here and automatically generate that list for us. No problem. Paste that in. And there you can see from 1 to 500, these are the only numbers that are both divisible by 13 and 9. So we can do all kinds of crazy filtering inside of Haskell. It's really cool and extremely powerful. We could also come in and create a sorted list. So let's go sorted list is equal to, we're just going to type in sort, and then we could type in a whole bunch of things that are out of order. Sorted list. And there they go. Now they're in order. Another thing you're going to use a lot is if, let's say, we want to combine lists. Well, we could go sum of lists like this. We could also go zip with, very powerful function. And let's say that we want to add all the values, create a new list based off of the values in these lists. So there you go. And there we are. Sum of lists. And there you can see it went and added all these different values and then created a brand new list called sum of lists. Zip with is very powerful. We're going to see more about it later on. We could also use filter, return a list of items that match a condition. So let's say we want list bigger than 5 equal to, and there's filter, and we want values that are greater than 5, and we can just go more primes or whatever we have here. And there you can see that popped that back. And we could also use a sort of while loop. So let's say we wanted to go and get the evens up to 20. We're going to use a function called take while. So we want values that are less than or equal to 20, and then we can use an infinite list in this situation. So you can see exactly how these infinite lists work. Up to 20, like that. And you can see it automatically generated that. And that's one way that we can use or demonstrate how Haskell is lazy. Went and created the list up to 20. It created this list right here, and even though this says infinite, it didn't go beyond that. So another example of what lazy means in Haskell. And then the very final thing I'm going to talk about here are fold L. What fold L is going to do is it's going to apply an operation on each item of a list. So let's say multiple of list, and we can go equal fold L, and the operation we're going to be performing is a multiplication, and put 1 here, and then 2, 3, 4, and 5. And what it did was it went through all these different list items from left, that's what the L part means here, to right, and multiplied them all together. And you could also come in here and change this to R if you want to go in the opposite direction. So like this, and you could say it came back to exactly the same thing because it didn't really matter. But that is how fold L, which does the operation from left to right, and fold R work, which does the operation from right to left. In some situations things will be different, but those are the way that those two guys work. So there's a lot about lists. I just want to take a second here and talk a little bit more about list comprehensions that are very important, which we've seen a little bit here already. Now, by list comprehension, all I mean is we're going to be performing certain operations on a list. So let's say that we're going to go and get power of 3 for our list. All we're going to do is put this inside of brackets, and then we can go 3n, where the n part is going to be the list items. So just want to make sure you really understand this because it's a very important concept. So there we can go 10, close that off, and what we're doing here is we're generating a list called power3 list. It's going to take each of the values out of our list here, 1 through 10, store them inside of there, perform this calculation, store them back inside of there. Just going to touch on this in a second. Power3 list, and there you can see it calculated those for us. And of course we can apply filters like you saw previously. And just for the heck of it, let's do another example. Let's say we wanted to generate a multiplication table by multiplying different values in different lists. So what we could do, let's go multiplication table is equal to, brackets here, and we're going to multiply x times y, and then we're going to define the value of y like this. We're going to be able to stack these up and use multiple lists in these calculations. So the value of y is going to be 1 through 10, and then the value of x for our calculations inside of here is also going to be 1 through 10. Close that off, and it's going to generate a new list called multiplication table. And we can go mult table, mult table, and you can see it went in there and created that multiplication table for us. So pretty cool. So there's a whole bunch about lists, and believe me, we're going to come back more to it here very soon. But let's talk a second about tuples, which are also very important. They're just basically are going to store a list of multiple different data types. A list, every item has to have the same data type. A tuple, that doesn't necessarily have to be true. So we could come in here and we could go random tuple like this, and then throw a 1 inside of there, and then go random tuple like that, and there you go. You just created yourself a tuple. Now what we're going to be using a lot are what are called tuple pairs. So let's go and create Bob Smith here. Go Bob Smith, and let's say that Bob Smith is 52. There you go. You just created a tuple pair for our Bob Smith information. Now we're going to be able to get the first value out of our tuple. So let's say we wanted to get Bob's name by just going FST and Bob Smith. And equally, we'll be able to get Bob's age by going SND like this, and Bob Smith, and Bob's name, and Bob's age. There we go. And another thing that's really cool is we can use zip, and what it's actually going to do is combine values in 2 different lists into tuple pairs for us. So we can go something like names, and then come in and create addresses, and then we could go names and address, and use zip to combine those into tuples. So we'll go names, addresses with zip, names and address, and look, it created a whole bunch of tuple pairs just by combining those 2 list items. Very important, zip, very, very important. We're going to see more about zip in a second. So I've been talking a lot about how Haskell is a functional programming language, but we haven't really created any functions, so that's what we're going to do right now. Another thing we can do is we can use let over here in the GHC. So you could say something like num7 is equal to 7, and then we could go let get triple x and create a function here, and then the value is going to be x times 3 in this situation, and then we could go get triple num7, and you can see we can do calculations over in the GHC as well. Another thing that's important is if we compile our program, we're actually going to be able to run it if we define everything in main. So let's go main, and then we're going to go do, and what do is going to do is it's just going to chain a whole bunch of different commands. and store them inside of main. So let's say we wanted to do something like print a string out. We could go put string ln like that and go something like what's your name, and this is just going to put a new line at the end of it, put string with that ln at the end of it. Then we could go name, and then we're going to store the value that they enter to name with this arrow symbol right here and get line. So that's going to take information from the console, and then we could go and print out information again to the screen and say something like hello. And then if we want to concatenate or combine these, we can do it just like that. Now we can come over here, jump out of this guy, and we would just go colon and a Q, and there you can see we just left. And then we can go GHC like this, dash dash make like that, and then Haskell dash tut, which is the name of my program. You can see that it compiled for us there. And then Haskell tut right like this. What's your name? Derek. And you're going to see that it printed that out in the terminal, or if you're in Windows, the command line. So let's get out of that and let's get back into the GHCI, and there we are back inside of there. And let's create a whole bunch of other different functions. So that's how we input and output information and compile things. Now what we're going to do is we're going to create a function that I'm going to call addMe. Now what you're going to do here is you're going to define the type declaration for your function, just like we did whenever we were typing in things like $t, so with the square root like that. That's a type declaration. So let's create one for addMe. So it's addMe, and it's going to be receiving an integer, and guess what? Another integer, and then it's going to be returning an integer. Okay, pretty simple. In the function name, the way that's going to work out, it's just going to be, or the actual creation of the function, it's going to be whatever you name your function, and then it's going to be any parameters that are passed inside of it, and then an equal sign, and then you're going to have all of your operations, and then a return value. And that is exactly how everything, let's spell value right, and that is how all your functions are going to be created inside of Haskell. So let's go and actually create our function addMe. So it's just addMe right like that. It's going to receive two values. I'm going to call them x and y, and then it is going to return after we perform this addition. So x and y are going to be our parameters, just like you can see right there. And then after your equal sign, you're going to have your operation. And this is also going to be the return value, right like that. And the data type that's going to be passed in is going to work if it makes sense. So if it follows this guideline, if it's an integer. It's very important to remember that every function must return something. It's also important to remember that functions cannot begin with an uppercase letter, which we're going to see why here very soon. And a function that does not receive any parameters, which we're going to see examples of those later, are going to be called a definition or simply a name. And of course, remember that we left our GHCI to go and compile our program, so we're going to have to go and get it again. So Haskell tut with L in front of it, and there it loaded it, and R. And now we're going to be able to come in here and go $t. And we can go addMe, and it's going to pop out our type declaration for us. And then of course we're going to be able to go addMe, and we could do pretty much anything we want. And you can see that it automatically went in there and added those together. So simple function. Now let's get a little bit more complicated. We'd also be able to come in here and not use a type declaration and just have Haskell figure out exactly what's going on. So we can do something like sumMe, and x and y is equal to x plus y. You can see that that still worked. However, now because we didn't define that we're only working with integers, we could actually come in and work with floats. And you can see that it's automatically going to work. We're also going to be able to come in here and add tuples together. So let's go add tuples, and we're going to define a type declaration here. We'll go int. It's going to receive a tuple with ints inside of it, and another tuple with ints inside of it, and it's going to return a tuple with ints inside of it. Don't let that confuse you. It's very simple. It's just going to have your parameters first, and then the final thing is going to be what's returned afterwards. So then we can go add tuples, and we can say we want x and y to be stored inside of there, and then x2 and y2. So there's the two tuples that we'll be returning, or we'll be receiving. And then we'll be able to create a brand new tuple, which is going to be made up of x plus x2 and y plus y2. Add tuples, and we'll just keep that really simple. And you can see that it added those together for us. We're also going to be able to perform different actions based off the values we receive. So let's say we go what age. Again, we're going to be receiving an int, and in this situation we're going to return a string. So we could say what age 16 is equal to, if they pass in 16, you can drive, is what's passed back. We could do this for a whole bunch of different things. So you could say at what age 18 you can vote, and 21 you could say something like, hooray, you're an adult. And then we could say what age, 18, and it pops back, you can vote. And we'll get more into those different things. You could also come in here and go what age, and just throw X inside of there to cover pretty much anything else, and say something like nothing important. So in that situation, if they say what age, and you say something like 40, nothing important pops back. Likewise, you could just put an underscore right here, which is very important, it's used a lot. What age, 56, nothing important comes back as well. Let's talk a little bit about recursion, because you're going to use that a lot. Let's go and create a factorial, and this guy's going to be receiving an int, and it's going to be returning an int. Here what we're going to define is all the different things that we could possibly do. So let's say factorial, let's say that they pass in a 0. Well, we're going to define that we want to return a 1 in that situation. Otherwise, we want to say factorial, if they pass in anything else other than 0, we're going to go and get that value, and we're going to multiply that times factorial, which is the function. We're going to be calling the function again, and then we're going to be subtracting 1 from the value of n that they pass inside of it. Seems really complicated, but it's not. So let's just save it, and we'll go factorial, and just keep this really simple and set it for 3. You're going to see that 6 pops back. So what exactly is going to happen here? Well, the first time through our program, we're going to pass in the value of 3. And what's that going to do? Well, it's going to multiply that times whatever the factorial of 2 is. Next time through, which is going to be this call for factorial right here, we're going to be passing in a value of 2, which is going to be multiplying that times the factorial of what? 2 minus 1 is 1. And then the last time through, we're going to be passing in a value of 1, which is going to be multiplying that times whatever the factorial of 0 is. Well, what is the factorial of 0? When 0 is passed in, this is going to give us a value of 1. So this is equivalent to 1. So this is going to be 1 times 1 is equal to 1. Okay, fine. So this value of 1 is going to be passed up inside of this guy right here. So this becomes 1. So what's 2 times 1? Well, that's going to be equal to 2, of course. So then we're going to take this value of 2 right here, replace it with that guy right there, and we're going to get 3 times 2, which is going to be equal to 6. Okay, so it's sort of like a backwards way of moving up until we get a final answer. And that's just a simple example of how we could use recursion inside of Haskell, which we use a lot. Of course, we could also come in here and calculate factorial by just using the product. So let's go product, fact like that, pass in a value of n is equal to, and we could go product, and then let's say, well, we can just go 1 up to whatever the value of n is. And there that is, product fact, pass in 3, and 6 comes back. So that's a really simple and easy way to do factorials, if you were wondering. We're also going to be able to use things called guards to provide different actions based off of different conditions. So let's create type declaration here, and let's call it is odd. It's going to return an integer, or it's going to receive an integer and return a boolean, and then we'll define what's going to go on here. So we'll say is odd, it's going to be receiving n. Then what we're going to do is tab that in, and this is the guard part. If n, and then we'll do a modulus on this as well with infix, so we put those back quotes inside of there, 2 is equal to 0, well then we're going to return a value of false. So what this is saying is if the value of n that they passed inside of here, whenever we take the modulus using 2, if that comes out to a value of 0, then we're going to return a value of false. So that means it's even. That's what this is saying right here. We're saying if it's even, return a value of false. Obviously, if we're checking if it's odd, that makes a lot of sense. Then we can come in and go otherwise, like this, return a value of true. So if we know that it's not even, well, obviously true is the answer we want to use here, and otherwise allows us to basically catch everything. It's a default. What's even more interesting is we could go and do something like is even n is equal to, we could shorten this a lot, mod 2 like that equal to 0, but I wanted to talk about guards because guards are important, and I definitely wanted to talk about that. So Let's come in here. We'll do more with guards here in a second. So we can say is odd, and then we could say 67. It's going to come back as true. If you just wanted to check is even and see if it actually works, yes, it does indeed work. So it's just two different ways that we can do that, and that's the way the guards work. Let's go and use something with guards that maybe makes a little bit more sense. We could say something like what grade, and this is going to receive an integer like that, and it's going to return a string. Now let's define it. So we could say something like what grade, and they pass in an age. Then we can use a guard here, and then we're going to throw in a condition. So if the age is greater than or equal to 5, and then we could stack this up and say something like age is less than or equal to 6, then the string we're going to return, remember we're returning a string, is going to be kindergarten. And then we could do this for a couple more of these guys. This, and we could say if age is greater than 6, age is less than or equal to 10. I'm just making this up as I'm going along here. I know I'm getting the kindergarten part right, but I'm not sure if I'm getting the elementary school part right, so whatever, bear with me if that's incorrect. And let's just go like this. Let's change this to 10. And let's change this to say 14, I don't know. And let's say that this becomes middle school. And then here we'll say 14 and less than or equal to 18. And this is high school. And then of course we could come in and put otherwise. And this string we're going to return is go to college. So there's maybe a better example of how we can use guards. And it compiled, beautiful. And we could say what grade, and then we could say 14, and it's going to pop back middle school. And we could say what grade, and we could say 56, and it says go to college. So everybody's going to college. Alright, so there's another example of how we can use guards inside of Haskell. Another thing that's neat is the where clause whenever we use it with guards. So let's do like a little bit of a baseball thing here. What where is going to do is it's going to keep us from having to repeat a calculation over and over again. So let's say we want to go batting average rating, and we want to rate players based off of what their batting average is. Well, in this situation, this is going to receive a double and another double, and it's going to return a string. So then we can actually create our function here now that we defined what it looks like. So batting average rating, and it's going to receive hits and at bats. Those are the two guys we're going to get. We're going to use guards here, and we're going to say average. You're saying, oh, what's average? Well, we're going to define that in a where clause. So if average is less than or equal to, and remember we got to put a 0 in front of there, 200, well then we're going to return a string that says terrible batting average. And then we can go average and say less than or equal to 0.250, and we could say average player, and then average less than or equal to 0.280, and we say you're doing pretty good. And then otherwise, well, that means the player is doing pretty doggone good. Their batting average is above 280 because this is catching everything underneath of there. And you can say you are a superstar. Well, now comes the where clause. And this is where we're going to calculate average, so we didn't have to calculate it every single time inside of there. And we're going to say where average is equal to hits divided by at bats. So there we are. Now there's the where clause. And we could go batting average rating, and we could pump in something like, we have to do hits, so let's go do something like 20, and then at bats is 100, terrible batting average, and then we could come in and change this to 30. You're a superstar. So you can see there's not much difference between a superstar and a terrible batting average in baseball, and more importantly you can see how guards and where work. And now let's take a look at how we can access list items in pretty interesting ways. So let's go and create another function. It's called get list items, and it is going to receive a list made up of ints, and it's going to return a string. And then let's define what's going to happen here. Well, if get list items is passed an empty list, it's going to pass back your list is empty. And then we can define everything else we wanted to do. List items. And in this situation, let's say that we just wanted the first value outside of this. We could say x and then colon like that, and then we could say something like your list starts with, and then show is going to change anything into a string, so we'll be able to output that on our screen. So that's one way to access this value right inside of there. And then we could go get list items, and let's say we wanted to get the second item in a list. Well, we would just put x and y, and there's the rest of the list items. is equal to your list contains, and then we could do a whole bunch of shows, show x, and then combine this again, and show, and then if we wanted to get the second item in the list, we could just go show y. And then another thing we'll be able to do, get list items. You're going to see this a lot. We want to get the first item here out of our list, and then the rest of the items, xs, is going to represent the rest of the items in our list. And then we can say the first like this, item is, and we can get x like that, and the rest are, and then use xs to get the rest of those items. Let's save that, everything compiled, get list items, and then we can pass inside of this, right like that. First item is 1, and the rest are 2, 3, and 4, and 5. And you can say that it went and got this guy and printed all those out for us. So those are different ways to access different list items inside of here using these guys right here. And we would also be able to come in here and get values with what's called the as pattern. So let's just real quickly go get first item, is the name of this, and it's going to receive a string, and it's going to return a string. Now I just need to define what it's going to do. Get first item, and if it doesn't, they don't send anything, we'll just go empty string. And if they do pass in something, we can go all at, and then x colon xs, like that, and then go equals, and then the first letter in, and we could go all, which is going to show everything that was passed inside of it, and then we could say is, and then if we want to get an individual item out of there, just go plus plus and x. Get first item, and then we can pass in a string, and the first letter in hello is h. So there's a heck of a lot of information about functions. Now let's take a look at higher order functions. And it sounds really complicated, but all this entails is passing functions as if they were just regular old variables. So let's create a function here called times4. Going to receive an integer and return an integer. And all times4 is going to do is get x. And then for the return type, it's going to get x times 4. So there we go. We went and created a function for ourselves. Let's go and put that together. Now what map is going to allow us to do is apply a function to every item in a list. So list times 4 is equal to map, and we can call times 4 and then have it multiply all that stuff against a list item or a list. List times 4, and there you can see it did that quite easily. We could actually come in here, you want to see how map works, we can go and make map. So let's do multiply by 4. What it's going to do is it's going to receive an integer list, and it's going to return an integer list. We could then go mult by 4, and if they pass us an empty list, we're going to pass back an empty list. And now we could go mult by 4. And we're going to be getting a whole bunch of different list items. We don't know how many, so in those situations you very often use x and xs if you're going to be processing a whole bunch of these guys. So like this, and we'll go times 4. We're going to be calling this function that we created right here. Times 4 receives a value, and then we're going to be able to go mult by 4 and pass it the rest of the items on our list. So what's going on here is the first value off the list is going to be x. So there, that takes that and it's going to pass it to the times 4 function up here. It's going to multiply it times 4 and it's going to store it in the new list item. Then what's going to happen is we're going to call multiply by 4 again with the rest. Remember that. This is the first list item. This is the rest of the list items. This is going to be passed back into mult by 4 again. The first value off of this new guy is going to be chopped off, and then it's going to multiply that times 4 and store it in the list. This is one of the concepts that I see students get confused about. So okay, first time we're getting into this function. Let's just keep it nice and short. First time we come through here in mult by 4, the value of x is going to be equal to 1. xs is going to be all the other stuff. So xs is going to be equal to 2, 3, and 4. So the 1's gone. So we multiplied 1 times 4, and then we created a new list item called mult by 4. That list, let's not worry about that. So what's going on here? First time this list is passed into multiply by 4, the x is chopped off, the value is 1, and xs is going to be 2, 3, 4. Well, now we can take 2, 3, 4 down here, copy that out of there. Second time through, now we have 2, 3, 4. So what's the value of x whenever it's coming through here this time to be multiplied times that? Well, it's going to be equal to 2. and then what's the value of xs going to be equal to? That's going to be passed back into mult by 4. It's going to be 3 and 4. See how it's doing that? It's chopping those off. And it's going to continue doing that until there are no list items left. When there are no list items left, it is going to stop this operation. So that is how x and xs work inside of Haskell. This confuses people. Hopefully I cleared that up. I think it's very clear. If not, leave a question below and I will give another example. We're going to do more with x and s, but that is exactly how those operate. I just want to make that 100% clear. So we're going to be able to come in here, save that, and then go mult by 4, and we pass in a list item. So there, and there we are, and you can see that it multiplied all those different values by 4. We could also come through here. Let's do another recursion example. And this is one of the things that I think makes Haskell great for being good at other programming languages, because we do a lot with recursion, but I think Haskell does recursion very well. So let's say if we wanted to check if strings are equal using recursion. I'm going to do a whole bunch of different examples here. So are strings equal? Well, we're going to first off define this. So we're going to be receiving a character list, which is what a string is, and another character list, and then we're going to say are they equal, which means we're going to be returning a bool. Well, let's define exactly what this is going to do. Are strings equal? Well, if they pass in 2 empty lists, well, the answer is going to be true in this situation, or at least that's what we want. Are strings equal? Here we're going to be checking a whole bunch of different values, so we're going to be using x and xs. But we also want to be able to check 2 lists, so we're going to be using y and ys. So we're going to come to our answer by just checking if x, this guy, the first item in our list, is equal to y, the first item in our second list. And because there's more than one character inside of here, we're also going to call our R strings equal again, and we're going to pass in the values of x, xs, and ys, which are all the remaining unchecked rest of the values in our list. Pass that back in there, and it just slowly cuts down the size of the list until it's empty. There's none left. And then finally we can say R strings equal, like this, and for anything that isn't an empty list or isn't a list item, we're going to cover this by just saying false, because we're angry and they shouldn't have passed in garbage into our function. And we compile that, and then we can say R strings equal, and we can pass in hello, and then we can pass in hello again. And you can see that it comes back true, and then hello, and then we can say you, and you can see it comes back false. So I just want you to really understand this, because I think this is the thing, based off of talking to students, that confuses them about Haskell. And it shouldn't, because it's easy. It's a little weird, but it's not that hard to figure out. I'm sure you guys get it. So now let's say we want to pass a function into a function, because we said we wanted to do that. So let's do multiplication. And here what we're saying with int and int is that we expect a function to be passed inside of this function that is going to receive an integer and return an integer. And then after we do that, we're going to return an integer. So this is defining a function that is going to be passed into our function. So we can go do mult and func, where func is equal to 3. Actually, the function I want to pass inside of here is times 4, so let's throw that in there again. So the function that's going to be passed inside of here is going to be times 4, and then it's going to take that function and pass 3 into times 4. Okay, so that's all that's saying right there. And we can actually do this. Let's just go number 3 times 4 and call do mult and then pass times 4 inside of it. And yes, that's legal. We can do that. So we're saying this in essence is going to store that value for us. There we go. And you can see that 12 pops back. So all we did was we defined a function called times 4. We passed that into this function, which we have right here. Passed that inside of there. Then this function, its job is to take the function that was passed in, which was times 4, pass 3 inside of it. 3 times 4 is going to be equal to 12, and then it stored that value inside of here and printed it out to the console. So that's how we can receive functions, but we can also return a function. So let's create another one called get add function. It's going to receive an integer, and it's going to return a function that's going to receive an integer and return an integer. We can pass the values into the function, so we can go get add function xy is equal to x plus y, and then we could go and define a function that adds 3, for example. So let's say adds 3 equal to get our add function. It's going to get 3, so it's going to take this 3 right here is this guy right here. And then what it's going to do is it's going to return that function and then store it inside of adds 3. Now what we could do is 4 plus 3 is equal to adds 3 and then pass 4 into that. And if we do that and run it, we could say 4 plus 3, and it's going to give us the value of 7. So there's an example of how to return a function from a function, and one weird way we can use it. One thing is neat is we could of course use this with map as well. So let's say 3 plus list is equal to, and call map, and then go adds 3, and then have it work on a list for us. 3 plus list, and there you can see that worked for us. And now let's take a look at lambdas real quick. Lambda, just to keep it very simple, is just a way for us to create functions that don't have a name. And so let's say we wanted to go double 1 to 10, and we could just create map, which is just going to execute a function on a list for us. How we define a lambda that doesn't have a name, so just put a backslash like that. X is what it's going to be receiving. What it's going to be returning in this situation is whatever the value that was passed into it times 2. And then in this situation, we can just pass inside of there a list from 1 to 10 and double 1, 2, 10, and there you can see it did that for us. Just a real quick example of using lambdas. Not that complicated, so I don't see any reason to focus on them too much because I have a whole bunch of other things to do. Let's also talk about conditionals. Now there's comparison operators, which we've seen already. So there's less than, there's greater than, there's less than or equal to, greater than or equal to, and then not equal to, which is a little bit weird. It's a / and equals. And we already saw the logical operators are going to be and, or not. And I already showed you exactly how those are going to be used inside of Haskell. You could actually use if statements inside of Haskell, or even though they're not used quite so much. We can go double even number, for example, and we can pass in y to this, and then we could say something like if y, and then let's do an infix here with mod 2 not equal to, let's just use not equal to here, 0. Always you have to have an else if you're going to be using if inside of Haskell. Then we're going to say then y, otherwise y times 2. And this is going to do exactly what it says. It's going to double only the even numbers, and it's not going to double the odd numbers. So we could say double even number, pass in 100. You can see that that worked. However, if we come in here and change this to 101, it's just going to pop back 101. So there's an example of using if, then, and else. You could also use case statements. So let's say something like we wanted to use get class. This guy is going to receive an integer and then return a string. And then we can say get class, go n, which is the value it's going to be received. And then we can say case n of, and here we're going to define our conditions. If it's 5 that they passed inside of it, go to kindergarten. If they passed in a 6, we would define go to elementary school. And then if we wanted to catch everything else, we could just put an underscore inside of there like that. Go away. There we are. Get class, and we could say 6, and you could test everything else. So there's an example of conditionals. Now we can briefly go over modules. These are modules up here that we loaded, of course. I'm just going to do a real quick example. Basically, a module is just going to contain a whole bunch of functions that you're going to be able to use in your other programs and load them. Well, you already know how to load them with import. And to create one, you're basically just going to have all of your functions inside of another program, another file. And then at the very top of the module, you're going to type in module, and you can say something like samp functions, like that, and then you're going to list all of your functions that you're going to have inside of your module, so even numbers, whatever they're going to be, and then you're going to type in where, and then you're going to have all of your functions listed. And then if you wanted to import this guy into your program to use it, you're just going to type in import and sample functions. Okay, so there's modules, pretty simple. Now let's talk about numeration types, which are basically going to be used when you want to define a list of possible types. And to create a enumerated type, you're going to type in data, and let's say I want to do baseball player, and then define all the different types of baseball players I could have. Well, I'm going to have pitcher, and I could either have this on one line like this, or I could put this down here like this if I'd want to, if it looks a little bit neater. There we go, looks a little bit nicer. You can do whatever you want. And you could say infielder, and then we could say outfield. And then if you want this to actually print out like a string, you would type in deriving show. Remember, show converts whatever into a string that we can use. Well, there you go. You're going to see more about deriving show here in a second. It's going to make a lot more sense. then you'd be able to do things like Barry Bonds, define that, and baseball player. And this is going to pass back a bool, and you could go Barry Bonds and define that Barry Bonds, being an outfielder, gets the value of true. This would then allow you to say something like Barry in outfield is equal to print Barry Bonds outfield, like that, Barry in outfield, and it comes back as true. So there's enumerated types. Now let's talk about custom types. Now with a custom type, you're going to be able to store multiple values, sort of like a struct, to create a custom data type. And to do so, you're going to type in data, and let's say we wanted to do something like customer. Of course, put a space between here. Then you're going to type in customer again, and then you're going to find all the different types that you want inside of it. So let's say we want 2 strings and a double. Once again, you're going to say deriving show, which just means we're going to be able to use this as a string. You're going to see here in a moment exactly what that means in a lot of detail. Now we'd be able to create a new type here using our custom data type, which is customer. And then to set the values for it, we're going to pass in customer and then some information about that customer. So let's say that first name, or the whole name, the address, and a balance that they owe us maybe. We could then come in here and define a function that's going to work with this, like get balance. And what we're going to say here is we want to find the right customer by passing in the customer's name. And to do that, we just say customer. And then what it's going to do, of course, is pass back a double, which is the customer's balance. Now to get that balance, what we're going to do is go get balance like this, and then we're going to pass in customer inside of it. We don't care about the name or the address, so we're just going to put 2 underscores there and have B represent the balance, which we do want, and then pass back balance. Now what we could do is just come in here and run that, and we could say get balance for Tom Smith, and it's going to return Tom Smith's balance for us. Do something a little bit more fun here. Let's go and create another data type. So let's say we want to play rock, paper, scissors. So RPS is equal to, and all the different types. This is just an enumerated type like we just saw a second ago. So rock, paper, scissors, like that. There we did. Create a custom type. And then we could say something like shoot RPS, RPS, and then it's going to return a string for us, depending upon the input that we provide. Then we define all of the ways that we are going to answer. So we'll say if we get paper and rock, what we're going to pass back is paper beats rock. And then we could do that for all of the other different things. And then if we want to do a catch-all that's going to catch if they pass in anything except what we expect, shoot, and there we go. And then we could print something like error out on the screen. And now we'll be able to come in here and go something like shoot, paper, rock, like that, and it's going to say paper beats rock. And of course if we said bullet, rock, it's going to go and mess that up because it doesn't have any idea what bullet is. Okay, so there's a quick example of how to implement rock, paper, scissors inside of Haskell. We could also define 2 versions of a type. So let's say we wanted to create a shape type that's going to work for both rectangles as well as circles. Well, we could come in and go data, shape, like that, and then define circle, and a circle is going to receive or contain 3 floats, while a rectangle is going to have 4 floats. So first 2 and first 2. And what this is going to represent for us is the first 2 floats for our center are just going to be the x and y coordinates, and the last one's going to be the radius. And then for our rectangles, we're going to have upper left hand corner coordinates x and y, and the bottom right hand corners x and y. Now if we want to be able to print these out, we're going to go deriving show again. Now what we could do is define an area function that's going to receive a shape and return a float. And how it's going to calculate is if it gets a circle, we can just take the radius for it and then go pi times the radius squared. And then likewise we could go area. If we get a rectangle, we can go x, y, x2, and y2 coordinates that are going to be passed inside of it, and then go get the absolute value of x2 minus x times the absolute value of y2 minus y, and it's going to perform the right calculation depending upon the data type that's passed in. Another thing that's important to remember with Haskell is you're going to see dollar signs a lot, and what that means is we want to get rid of these parentheses. So if you want to get rid of those parentheses, you would put a dollar sign inside of that and then get rid of that, or a dollar sign right here and then get rid of that. So that's all the dollar sign does, is it gets rid of parentheses. And that just means that anything that comes after it takes precedence over anything that comes before it. And of course, make sure we come up here and call that circle. Spell that right. And I'll let you play around with that on your own. Let's also talk a moment about the dot operator and how that works. Basically, it's going to allow us to chain functions to pass output on the right to the input on the left. So let's say we wanted to go some value and put string length, which is just going to print stuff out to the screen. We could go show like that. 1 plus 2. Okay, that's one way to do it. Another way to do it with a dot operator is to go some value. Let's just call it 2 so that it doesn't freak out at us. It's the same thing. We could also go put string length like that, dot, show, and then let's use the $sign as well. We could go $sign 1 plus 2. So that's just a way for us to be able to chain those values together. And then we can go some value 2, and of course it's going to give us an answer of 3. And we could also come in here and go and get the area of our circle just by going area like that, and it's a circle, and we'll go 50, 60, and 20. And then likewise we could do area of rect is equal to, and then we can call area, and what the heck, let's do $sign again, just so you're used to that. Rectangle, 10, 10, 100, 100, area of circle, and area of rect. So that's how we can perform some custom types or create custom types and a whole bunch of other different funky little operators that are special to Haskell. Now let's take a look at type classes. Now type classes are going to be things like num and equals and ord and show. Remember I kept saying we're going to talk about show? Well, now's the time to talk about it. Those are type classes. And type classes are going to correspond to sets of types which have certain operations defined for them. So for example, our addition operator is going to work with parameters that use num, and you can actually see that if we come over here and just go t plus, there you go. You're going to see that it works with nums, and that's a type class. And that what this is basically saying here is for any type A, so it could be ints or doubles or whatever, as long as it's an instance of type num or type class num, we're going to be able to add it. Okay, so that's what that's saying. And of course it also says that it's going to take 2 values and return 1. Of course, that are also all going to be of type num. So what we can do is we can come in here and let's say we want to create a custom data type of type employee equal to employee, and it's going to receive a name string, a position, which is also going to be a string, an ID number, which is going to be an integer, and then what we can say at the bottom of it is deriving EQ and show. So we're going to be able to show that these employees, because we're defining it here, they're first off going to be able to be shown as strings, but also they're going to be able to check for equality between them. Okay, so we have those defined, so we can create 2 employees. So let's create Sam Smith and Pam Marks. And you can see here I defined the names and the position and the ID numbers for them. So we could save those, and we could also come in here and go is Sam Pam equal to Sam Smith equal to Pam Marks. Is Sam Pam comes back as false. And of course we could also print out all of this information by going Sam Smith data equal to and use show for this guy, because we said that we wanted to be able to use show, and we also wanted to be able to check equality. And Sam Smith data pops back all of that information for us. Now let's create another data type. Let's call this shirt size. Oh, and you may have noticed I'm now using uppercase letters for these guys. That's the reason why we can't use uppercase whenever we are defining functions. So we'll just have small, medium, another enumerated type for us, and large. Now we can actually define our type instances and how they're going to work with EQ and show. To do that, we go instance, EQ, like that, and shirt size, where, and now we'll define exactly what is equal. So if s is equal to this, or if we're asked that, we're going to return a value of true. Medium equal to medium, yes, that's going to come back as true, and we're defining or overriding what the EQ type class does for us, or says is true. Large equal to true, and if they ask us for anything else, we're going to say that it's false. And we could also define how show is going to work, so we'll go instance show, and we can override it and have it do whatever we want. Where, and in this situation, if they ask us to show s, what we're going to say is instead of s being displayed, we want small displayed. And if they want us to show m, we're going to say that we want medium to be displayed. Now we can do things like check if small is in a list, so we can say something like small available. We can go s, and elum is going to check if something's in a list for us, and of course in this situation it will be. We could also come in and go the size is equal to and call show s. Got a little bit of an error. Need to put an equal sign inside of there, and then we could say something like the size, and you can see small pops back, and we could also check small available, and you can see that that comes back as true. So that's how we can override or define those type classes. We could also define a custom type class that's going to check for equality. So let's come in here, create another one of these guys, class, and we're going to use my equal, use my custom guy. So where, and in this situation I'm going to say r equal, and here a is going to represent any type that implements the function r equal. So we're going to say r a da, 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 and in that situation we're going to return boolean, and then we can go instance for my brand new equals. What I was going to do is for shirt size. Let's just do it that way. Pop that in there. Where, then we'll say r equal, and if we get two smalls, we're going to pop back true. R equal, two mediums true, two larges true, and otherwise false. And now we'll be able to say new size and call r equal M&M like that, and new size comes back as true. So that's how we define our custom type classes. Now let's take a look at IO. So let's create a little function inside of here just to review. Remember, do is allowing us to chain a whole bunch of different things together. So we can go put string, what's your name, like I did before. I'm then going to be able to get keyboard input, putting that little arrow inside of there, and get line like that. Going to be able to output information. Again, get rid of the parentheses with that, and then we'll say hello, concatenate these together with name. Run that, say hello, like that. What's your name, Derek? Hello, Derek. There he goes, talks to me. So just a quick little review of how we're going to be able to get input and then output. And now let's take a look at file IO. So let's say we want to write to a file. Well, we would just go. It doesn't have to be write to file, it can be whatever. We're going to be chaining a whole bunch of functions, so we'll use do. We need to open a file that we want to work with, and we use open file to do that. And we pass in the name of the file that we want to open, and we want to write only to it. So we're going to say write mode. To put text into that file, we're going to go h put string line like that. Pass in the file handle that we have right here, which is this guy right here, and then we'll put inside of here random line of text. There we go. That's what we're going to write to our file. Make sure we close that off at the end, and then very importantly, make sure we close our file, release that. And that's how we write to a file. Pretty simple. If we want to read from a file, read from file is what I'm calling this. Can be called anything, of course. And then of course we're going to say let's go and reopen that file that we just created and wrote to. To open a file, for read mode we go open file, and we type in the name of the file we want to work with. Can work with any type of file. I'm using text files here just because don't have to worry about anything funky in regards to messing with them. If we want to get the contents of the file, we just go contents, and then we'll just say h get contents, our file handle, the file, and then we can say put string contents, and then of course just like before close our file. There we go, and it compiled, and we can say write to file, and it wrote to it, and then we could say read from file, and it printed it back out on the screen. So that's how we both write and read from files inside of Haskell. The final thing I wanted to cover here was a video actually done on YouTube that a lot of students have asked me questions about in the real world, so I thought I would cover it here. Now that piece of code actually generates the Fibonacci sequence, and how it does it is it goes equals 1, it creates a list with all the Fibonacci numbers inside of it, and of course you know this is the cons operator, which is going to combine these two values right here. And I'm going to go through this line by line and explain exactly what's going on inside of it, because I received a ton of questions about it. Alright, so you can look at this while I'm typing this out on the screen and see if you can figure out exactly what it's doing, and then what I'm going to do is actually explain what it's doing. Fib, tail, fib. So what this is doing is creating a list that is going to be made up of the Fibonacci sequence, and this is an equal sign. Sorry about that. Okay, so what's going on? You could pause the video and work it out yourself. Otherwise, I'm going to actually go through and talk about it and explain exactly what's going on. Fibonacci sequence, if you don't know, is going to be a whole series of values in which the two previous values are going to add together to make the next value. So then this goes to 3, and this goes to 5, and of course this goes to 8, and then this goes on forever and ever and ever. Alright, so how exactly does this create an infinite list of Fibonacci numbers? Well, this is basically creating a list from left to right. It's also using recursion down here, and it's using zip right here to create pairs using the contents from two lists and throwing them into a tuple. So what it's doing is it's starting off by creating our list, and that list is going to start off with the values of 1 and 1. There we go. And it's going to continue generating numbers. But from the very beginning, we have a list that has the value of 1 in the first index and 1 in the second index. Now we come down to this guy right here. What this is saying is zip, let's take the fib, which is going to be 1 in this situation, and the tail of that fib, which is going to be this value of 1, and let's pass it over here to this function. So all this is saying is it's going to receive an a value, which is going to be this right here, or this guy right here. And then this is going to receive the tail part, which is the rest of the list, which is going to be passed into there. It's going to add those together, and it's going to create the next item in our list, which is going to be 2 in that situation. So, just to reiterate this guy, the first time through fib, let's say first time, fib is going to have a value which is going to be equal to 1, and tail fib is going to have a value which is equal to 1. So the list is now, after the first time through, going to be 1, 1, and 2. And the reason why is going to be because A is going to have a value of 1, and B is going to have a value of 1, which is going to give us a final value of 2, which is going to be stored in our fib list. Remember, this list is going to be created from the left to the right, so you can almost see this slowly expanding on its own. This is generating the rest of the list. Second time through, fib is going to have a value of 1, which is going to come from this guy right here, and tail fib is going to have a value of 2, which is this guy right here. So after we go through that the second time, we're going to have 1, 1, 2, and 3. And that is how it is going to expand itself. And the reason why is A in this situation is going to be equal to 1, that guy right there, this guy right here, and B is going to be equal to 2, that guy right there, and that's how we're going to get our 3. Now by doing it this way, what we're going to do is we're going to be able to come in and do something like fib 300 is equal to fib, and let's say we want the 300th Fibonacci number. We're going to be able to get it by going fib 300, and there you can see. And you can also see how giant numbers can be inside of Haskell, which is pretty ridiculously cool. And then of course we could also come over here and say take the first 20 fib numbers to get those. Okay, so hopefully I explained that pretty awesome example that's on YouTube, but I get asked about it all the time, so I thought I'd cover it at the end of the video. So there you go, guys. There's a heck of a lot of information about Haskell. Please leave your questions and comments below. Otherwise, till next time.